Parallel programming enhances computational efficiency by dividing tasks across multiple processors. Open multiprocessing, a widely used application programming interface, simplifies this process by providing a set of compiler directives, library routines, and environment variables. It enables developers to write parallel code for shared memory architectures, optimizing performance and resource utilization. Parallel programming interfaces like OpenMP enable efficient multi-threading by providing a framework for developers to write code that runs simultaneously across multiple processors. This approach optimizes performance and resource utilization, crucial for complex computations. Understanding these interfaces is essential for leveraging the full potential of modern computing architectures. OpenMP is a programming interface designed for parallel computing on shared memory systems. It facilitates the creation and management of lightweight processes, enabling efficient workload distribution. OpenMP also handles synchronization, both explicit and implicit, and manages variable status, ensuring seamless parallel execution. OpenMP enables efficient management of lightweight processes, facilitating work distribution and synchronization. It handles variable status, whether private or shared, within a shared memory architecture. This programming interface is crucial for parallel computing, optimizing performance by leveraging multiple processors effectively. OpenMP operates on a fork-join model. Initially, a master thread is created to handle sequential tasks. When a parallel region begins, the master thread forks additional threads, forming a team. These threads execute concurrently, and upon completing the parallel region, the forked threads terminate, leaving the master thread to continue. The OpenMP API includes compiler directives for Fortran C++ library routines and environment variables. It offers user-friendly, incremental parallelization, allowing a single source code for both serial and parallel versions. However, it provides limited user control and is best for parallelizing loops, focusing on data parallelism. A shared memory program involves a single process, creating multiple threads. These threads communicate by reading and writing to shared variables, necessitating synchronization to prevent conflicts. The operating system manages thread scheduling, ensuring efficient execution. OpenMP facilitates this by providing a framework for parallelizing code, enhancing performance through shared memory access. OpenMP utilizes a shared memory model where threads communicate by accessing shared variables. Variables seen by multiple threads are shared, while those seen by one thread are private. This model can lead to race conditions, necessitating synchronization to prevent conflicts. Adjusting data storage can help minimize synchronization needs, enhancing efficiency. Multi-threading in OpenMP requires expertise due to challenges like deadlocks and race conditions. Its non-deterministic nature complicates debugging. Despite these challenges, multi-threading is a natural model where all processors share memory, allowing threads in a process to access the same address space. This has led to the development of numerous shared memory algorithms. A process must exist to create a thread, with each process having at least one thread. Processes have unique virtual memory spaces, inaccessible to others. Threads within a process share this space, allowing them to read and write to the same memory. They share process IDs, file descriptors, and signal handlers, but have individual program counters and stack pointers. OpenMP operates with a team structure, consisting of a master and worker threads. A parallel region is a code block executed by all threads simultaneously, featuring an implicit barrier. The master thread is always assigned thread ID 0. Parallel regions can be nested, and the if clause can control their execution. To make Hello World multi-threaded in OpenMP, use the parallel directive. This allows multiple threads to execute the print statement concurrently. Ensure each thread prints Hello World by placing the print statement within the parallel region. This demonstrates basic parallel execution, showcasing OpenMP's ability to efficiently utilize multiple threads. A parallel region in OpenMP allows code execution by multiple threads. Use the parallel directive to create it. Specify thread count with OMP set num threads n. Each thread executes the POIDA function, receiving a unique ID value, enabling concurrent operations on shared data. In a parallel region, all threads execute the same code, sharing the A array. This ensures data consistency across threads. Implicit synchronization occurs at the end of the parallel region, coordinating thread execution and maintaining data integrity. OpenMP compilers generate code similar to the example shown, utilizing a thread pool to avoid the overhead of creating and destroying threads for each parallel region. Typically, only 3 threads are created, as the last parallel section is executed by the parent thread, optimizing performance and resource management. In a parallel region, a thread forms a team, becoming the master with ID 0. All threads execute the subsequent code, concluding with a barrier. Data sharing attributes include shared, private, first private, default, thread private, last private, and reduction, each defining how variables are accessed and modified across threads. In OpenMP, shared variables are accessible by all threads, but require synchronization for consistent updates. Conversely, private variables are unique to each thread, initialized with undefined values, and don't need synchronization. Understanding these attributes is crucial for efficient parallel programming and avoiding data races. First, private variables in OpenMP are initialized to the original value, allowing each thread to have its own copy without synchronization. The default data sharing attribute depends on the construct. For parallel regions, it's shared unless specified otherwise. If none is set, the compiler requires explicit attribute settings by the programmer. OMP master executes code with the master thread only, without an implied barrier. OMP critical restricts access to one thread at a time. OMP barrier synchronizes all threads. OMP atomic updates a memory location atomically. OMP flush ensures consistent shared variable views. OMP ordered maintains sequential execution order. OMP single is executed by one thread with an implied barrier and flush. In OpenMP, a barrier ensures that all threads in a team reach a synchronization point before any can proceed. Every thread must encounter the barrier, maintaining a consistent sequence of work sharing and barrier regions. Implicit barriers occur at the end of constructs like do, parallel, single, and work share, ensuring orderly execution. Race conditions occur when multiple threads read or write shared data simultaneously, leading to unpredictable results. OpenMP offers solutions like reduction, atomic, and critical sections to manage these issues. Reduction combines results safely, atomic ensures operations are indivisible, and critical sections allow only one thread to execute a block at a time. Using OpenMP's critical section ensures only one thread executes a section at a time, preventing race conditions. However, this approach introduces significant overhead and serialization, slowing down performance. It's crucial to weigh these drawbacks against the need for thread safety in your application. OpenMP's atomic operations act as mini critical sections, offering mutual exclusion for single-line memory updates. They are hardware-controlled, resulting in less overhead compared to critical sections. However, atomics have certain limitations, as they only apply to the update of a memory location, ensuring efficient synchronization with minimal performance impact. OpenMP's reduction clause prevents race conditions by making the reduction variable private to each thread. It performs the specified operation at the loop's end. Supported operators include plus, star, minus, slash, ampersand, caret, vertical bar, double ampersand, double vertical bar, with min and max added in OpenMP 3.1 for C++. Operators cannot be overloaded in C++. OpenMP scheduling optimizes loop iterations with 4 strategies. Static assigns fixed-size chunks round-robin. Dynamic allocates chunks as threads complete tasks. Guided reduces chunk size exponentially, maintaining a minimum. Runtime allows dynamic determination via environment variables. Each method enhances performance by efficiently distributing workload across threads. In OpenMP, loop iterations can be scheduled using various strategies. Static scheduling assigns fixed-size chunks to threads in a round-robin fashion. Dynamic scheduling allocates chunks as threads become available. Guided scheduling starts with large chunks that decrease exponentially. Runtime scheduling allows the environment to determine the strategy and chunk size dynamically. In OpenMP, loop iterations are divided among threads. Unlike message passing interface, where manual distribution is required, OpenMP allows the compiler to decide. By default, it often selects static scheduling, distributing chunks of iterations evenly across threads, with each thread handling NP iterations, where N is the total number of iterations and P is the number of threads. In OpenMP static scheduling, you can specify chunk sizes for loop iterations. The compiler assigns these chunks to threads until completion. However, if the chunk size isn't a multiple of the loop's total iterations, it can lead to threads having uneven workloads, potentially causing inefficiencies. When loop iterations vary in execution time, static scheduling can lead to load imbalance. Some threads may finish early, leaving others to handle longer tasks, resulting in idle time and inefficient resource use. This imbalance can significantly affect performance, especially in heterogeneous workloads. Dynamic scheduling in OpenMP assigns chunks to threads as they become available, allowing for better load balancing. Once a thread completes a chunk, it receives another. However, this approach incurs higher overhead compared to static scheduling, as the system must continuously manage and assign tasks dynamically. OpenMP examples illustrate practical applications of parallel programming. Consider a loop parallelized with OpenMP, where each iteration is independent. By using the parallel for directive, tasks are distributed across threads, enhancing performance. This approach is crucial for computational tasks, ensuring efficient resource utilization and reduced execution time. OpenMP provides an API for library calls that perform essential functions in parallel programming. To utilize these functions, include omp.h in your code. Remember, your program won't compile without OpenMP compiler support, ensuring the necessary parallel processing capabilities are available. To compile an OpenMP program, use commands like gcc, fopenmp, o-myprog.c for C or g++, fopenmp, o-myprog.cpp for C++. Ensure the fopenmp flag is included to enable OpenMP support. For object files, use g++, c myprog.cpp, o-myprog.o, fopenmp. To compute P using OpenMP, we employ a numerical evaluation of an integral via the rectangle method. This involves dividing the area under a curve into rectangles, calculating their areas, and summing them. OpenMP efficiently parallelizes this process, distributing the workload across multiple threads to enhance computational speed and accuracy. False sharing occurs when independent data elements share a cache line, causing inefficient cache usage. To mitigate this, use padding to ensure elements reside on distinct cache lines. However, padding requires a deep understanding of cache architecture. Exercise caution to optimize performance effectively. To compute PI using OpenMP, employ the OMP for reduction directive. This approach efficiently sums partial results across threads, minimizing synchronization overhead. Ensure each thread independently calculates its segment of the series, then combines results using reduction. This method enhances performance by leveraging parallelism while maintaining accuracy in the computation of PI. In OpenMP, calculating Fibonacci numbers involves parallelizing the recursive formula fib_n cas fib_n1 plus fib_n2. This approach efficiently computes each Fibonacci number by distributing tasks across multiple threads, enhancing performance. For instance, fib0 and fib1 both equal 1, serving as base cases. This method optimizes recursive calculations, crucial for large-scale computations. Quicksort is a highly efficient sorting algorithm using a divide-and-conquer approach. It selects a pivot element and partitions the array into two subarrays, sorting them recursively. Open multiprocessing can parallelize this process by concurrently sorting subarrays, significantly improving performance on multi-core systems. The Gauss-Seidel method iteratively solves linear systems, specifically AXB, by refining approximations of unknown variables. It updates each variable sequentially, using the latest values, enhancing convergence speed. This method is particularly effective for large, sparse systems, making it a valuable tool in numerical analysis and computational mathematics. Cholesky factorization decomposes a Hermitian, positive definite matrix into a lower triangular matrix and its conjugate transpose. This method is crucial for efficient numerical solutions in linear algebra, enhancing computational speed and accuracy in solving systems of equations. To optimize OpenMP performance, avoid serialization and refrain from using solder pragma OMP parallel for before loops. Employ reduction techniques whenever feasible. Minimize input-output operations and critical sections. Opt for atomic operations instead of critical sections to enhance efficiency. Thank you for your attention. We hope this presentation has provided valuable insights into optimizing performance with OpenMP. Continue exploring and applying these strategies for efficient parallel programming.